might still have. And I'll just kind of go through this. I'll start quickly. Slow me down if you have any questions on it. But I think when you see the little subtleties that some of you might have overlooked, you'll see it right away. Particularly in the part B, you'll notice that all of these had like a question A and then a question B. And question A was usually, or at least was supposed to be straightforward. And then B had a little more of a thought to it and a little bit more of a twist to it here. But I'll start with number one, this was supposed to, go ahead and put it right there. This is supposed to be the easiest one, but it too has a little bit of twist you want to be real careful with here. But here's the idea. You start off with a glass block. And so here's the glass block. And a beam of light is hitting at some angle as measured from the normal. Now, it's going to be difficult for me to put in numbers here, and so I was thinking about it this morning. I know what I'll do is I'll put in numbers and alternate tests so that some of the numbers will be yours, other ones you'll have to put in your own. But starting with the gold one here, this one said the angle was 45 degrees. For those of you who have the tan or the blue one, you have a different angle there. But if I put in this angle of 45 degrees, here's the idea. Here's the easy part of this problem was Snell's law. That if you put in n1 sine theta 1 equals to n2 sine theta 2, that's kind of this first step. You know we start in air and you're given the angle of incidence. Like I said, for the gold one it's 45, for the other ones they're a different angle. It goes into the glass block and they tell you the index of the glass block is 1.5. And after a little bit of arithmetic, if you're on the gold one, you come up with an angle of 28.1 degrees. And so that is the refracted angle. What's important to then do from here is to realize where is it going to hit. And so the angle, of course, is more towards the normal, so it does not continue on at its 45 degrees. It does bend towards the normal. Your first question would be asking, does it hit here on what I called face C, or does it hit here what I call face B? And so you're going to need to do a little bit of trigonometry at this point. Since this angle is 28.1, then this angle here is 28.1. At least on the gold one, the size of the cube is 5 centimeters. So this distance is 2.5. And if you call this distance down x, that would kind of be my question. Does it hit face C or does it hit face B? So like I said, I think this is probably the easiest step in the problem. The next step, and certainly not the hardest one yet, but the next one is, where does it hit? Does it hit C or does it hit B? We know it's not going to hit over here at A, so we can rule that out, at least so far. But when we go through this math, in this case, the tangent of 28.1 degrees would be the opposite, 2.5, over the adjacent, which is x. So if I calculate x for this one, I get 4.68, which means it does hit way down here near the bottom for face C. And in fact, all of the tests hit face C. It doesn't exit there, so there's more to this problem, but it does hit face C at that point. Some of them a little bit closer to the bottom and some a little bit further up, but somewhere in that area. Now, knowing that much, now we have to ask, I think the hardest part of this problem is, does it exit here? And no, and you guys caught it. Most of you caught it anyways. No, this is beyond the critical angle. And so there's the next part of this is to realize that there is this thing called the critical angle. The critical angle, we said, was when light is going from a dense material into a less dense material, it may reflect back in. It may have total internal reflection. And for any angles greater than the critical angle, that will happen here. The nice thing about this is if you don't realize it's a critical angle and you try to put in your numbers, you're going to get something like the sine of the angle equaling something greater than 1. And it looks like many of you did, because I saw the erasers going, uh-oh, that's not going to work here. And you're right. It won't work. It can't exit. You can't have sine of an angle greater than 1. Unfortunately, some of you fixed the problem by just switching the angles and getting it less than 1. That didn't help. It still doesn't come out at C if you switch your angles there. So don't just play with the angles to make the math work out right here. There's a reason why there's not an answer for it coming out at C, because it doesn't come out at C. So don't try to apply Snell's law here. You could do a quick calculation of the critical angle. And the critical angle, I think it came out to be 41 degrees. I don't have it on this one. But yeah, it's 41.8, and it would be the inverse sine of 1 over 1.5. So there's your idea of the critical angle that we went through. Okay, so that's, like I said, is the part where I think the problem got hard. It's like, uh-oh, it doesn't exit there, does it? No, it doesn't. So it reflects. And so it's going to reflect and head down. And again, if you wanted to go through some trigonometry to make sure it hits B and not goes across to A, you can. But I think this one is so close, and this angle is so large that it's probably obvious it's going to hit B before it does anything else. Of course, we should probably ask, again, is that beyond the critical angle? And no, the answer is no to that one. In fact, as we look at the angle, we can see that if this is 28.1, this is the complement of that. Since the angle of reflection is equal to the angle of incidence, that too is the complement of 28.1. And then so this angle is the complement of the complement. So we're back to 28.1. And so I know that that angle is just a 28.1. And then it's just Snell's law in reverse. So not a surprise when it's all said and done, I'm back to the same angle it went in, which for the gold paper is 45, for the blue paper it's 60, the tan paper 55. Yeah.
Is there ever a situation that it would bounce twice in a corner like that?
No. Yeah, not for a nice cube like this. No. I mean, there's other geometric shapes that the answer could be yes, but not for this one. Yeah. So anyways, the answer is it does come out at B, and the angle is the same that it went in.
I thought the book says that the reflecting paints or whatever are squares. Parallelogram.
Reflecting. Reflecting. Yeah.
Is that two internal reflections?
No, they're not internal reflections. They're actually polished and reflecting material. The corner reflectors. Yeah. All right, well, good. As you guys are coming in, make sure you grab your test. I'll go on to the second one, and I'll do this one in blue. Yeah. Oh, because it is more than or it is less than the critical angle. So the critical angle was 41.8. So anything that is less than 41.8 refracts and comes out. Anything greater reflects and goes in. And so that's why this angle, I guess I didn't actually calculate it, but the complement, I think I have it on here, is 61.9 degrees. And so as it hits face C, it is definitely greater than the critical angle. Okay. And this is one example, actually this whole test is one good example of, you can't just blindly plug and chug into these problems. You got to stop and pause and look a little bit more at the physics of it. And this is a good one. If you just try to take the 61.9 degrees and apply Snell's law to it, of course you'll get, like I said, sine of the angle greater than 1, and that should bother you in and of itself. But, the fact that you're even doing Snell's law is a little bit, fact that you might have missed some important piece of the physics there. Anyway, so like I said, it does exit at B and ends up coming back out at the same angle. I suppose I should have put the block maybe on top of some other material so that the angle would still be different and make another Snell's calculation. But that wasn't my intent. My intent was first Snell's law and then, if you would recognize, critical angle. Well, let's go on to B. B, I think it's a little bit harder. Actually, you guys nailed B for the most part. It's a little long. Probably there, if any common mistake, is the fact that when it reflects, it goes back through the lens a third time. So don't forget to apply the equation 3 times versus just 2 times. And so the light from the candle goes through the lens, then it hits the mirror. As it reflects back through the lens, there is another formation of an image. And so we need to apply this 3 times. I'll start with the focal length. Hopefully the first thing you did was remember that in order to calculate the focal length, you need to know what the index of the material is and the radius, the radii of the 2 curvatures. So in this problem, we did say it was made out of glass, and the radius of curvature of each one was 10. Probably the thing to be real careful about, though, is your sign. As I mentioned in this chapter, that's probably the hardest part of any of our optics is making sure our signs work right, because our formula is all reduced down, which is nice, to the same formula again and again and again. But the justification of how that works is if we're willing to be careful with our definition of positives and negatives here. And so our radius of curvature for the second surface is a negative 10. And the first one is a positive 10. And so all of you, doesn't matter which test you have, should have a focal length of 10 for the lens. For the mirror, and maybe I'll just put the mirror, we learned that the focal length was half the radius of curvature. So that was, at least the first 2 steps that I did, was first get what's the focal length of my lens, and then what's the focal length of my mirror. And in this case, they said that the radius of curvature was 15, and this is in centimeters, I should point out, centimeters. And so this is a distance of 7.5. Keeping in mind, though, that this is a convex lens coming up here, and mirror. Well, it gets the convex lens too, but the convex mirror has the negative focal length. So watch that one. All right. So I don't know if you want me to put a negative yet, or now or later on, but somewhere along the line, when I definitely do my equation, I got to have a negative in there. All right. So my first step would to say 1 over P plus 1 over Q is equal to 1 over F, and that should find what I would call Q number 1. Where is the image from the lens, and the lens only? Well, like I said, I'll do these numbers in blue here, but for the blue one, you are told that the object is 50 centimeters to the left, and the focal length we just calculated. So in the blue one here, I get 12.5 centimeters. I also could think about the magnification of the first one as this Q with the negative over the P, which is a 50, and that gives me negative 1/4. So that lens by itself inverted it, made it smaller by a factor of 4, and it's this far from the lens. Well, so then when we try this equation a second time, because we're now going into the mirror, the image from the lens now becomes the object for the mirror. And again, the hard part might be getting this distance here, especially since the distance to the mirror is not this big. And again, it doesn't matter which test you have, this distance is greater than the distance you have to the mirror. In the case of the blue one, The mirror is, how far is the mirror here in this one? 6 centimeters. So if I go 6 minus 12.4, that would be the object distance. So notice a negative number. That was our virtual object. And again, that's what can make the problem hard, is when do we treat our signs as positive and negative. So this should be a negative number here, which of course this is a negative 6.5, again for the blue one. And again, notice I'm using a negative here for the focal length of the mirror. And if you do that, you will get Q2. And again, in the case of the blue one, it's a pretty big number. But all of yours, it's a pretty big number, and it's a positive number, which is what we want to keep in mind. I guess I didn't even draw it on the board here. You have it in front of you, but here's the situation. We've got this candle out here, and so the light has come in, and the image that would have been formed by this one would have been back here. But before it gets to that, it hits this mirror. And according to these numbers, that would have formed an image way over here somewhere. Again, further away from this lens. So, oh, and maybe I should do the magnification before I do it the third time. But the magnification then would be that negative Q2 over P2, which for the blue one is 7.5 times. And for the other ones, it's going to be a little different number here. But you can either A, work it out, or B, I'll let you see these numbers individually. But that's the magnification. It's just the third thing, don't forget also, is that you have 1 over P3 plus 1 over Q3 equals to 1 over F. And so now the light goes back through this lens to form the final image here. And so we need to get P3 again, but in this case, 48, and it's positive, means the image from this one is way over here. We already said this was a distance of 6, so I need to go 6 minus 48.75, and again, notice a negative number. It's a virtual object in this case also. Now it's going back through the lens, and we already calculated the focal length of the lens, and they're the same either direction, so that should give us Q3. Now again, the blue one comes out to be 8.1 centimeters, with a magnification then of 0.1896. All right, so we finally got what we were after. What is the final position as measured from the lens? That was one of the questions. The other question is, what is the size of it? And so the total magnification is what we've done to it each time. Then if we multiply it by its original size, which in the case of the blue one is 3 centimeters. The other ones were like 4 or 5 centimeters in there. But there's my total magnification, taking that one, and that one, and multiplying together, multiply by 3, and in this case, it's a negative 107 centimeters for the blue one. So it's upside down, and it is about a third the size of it when it got started. And other than being kind of lengthy there, I think you guys got the idea, and certainly could tell that you figured out that the object of the second element is the image from the first one. The only thing that's easy to overlook is that it's coming back a third time through there. But I know we went over it in class, and I think there was a homework one like that, wasn't there? That went through that way too. So it's hopefully any consolation. Now the tan one, which didn't have any extra tan one, so I had to do it on a regular sheet. So I forget even what the question is. Oh yeah, this is the 2 different wavelengths going through a double slit. experiment here. And so we're going to send this light through a double slit experiment. Hopefully you got the idea of, well, if it was just one wavelength, lambda 1, you would have had constructive interference down the middle, and you would have got another constructive at m equal to 1, and another at m equal to 2. And so our pattern would look something like this: m equals 0, m equal 1, m equal 2, m equal -1, m equal -2. Okay? Now that's just for one color. So another color, a shorter one, and actually I should look. Is the second one the shorter one? It is on this blue one. I think the second one is the shorter one on all of them. They're not necessarily red and blue in color, but to get them to color code here, I'm going to draw this in blue to represent a shorter wavelength. And so when the blue light goes through here, it too would be right here at m equaling 0. And so we would have an overlap right in the center. That's going to be part B question in just a second. But the shorter wavelength would mean that the constructive interference for m equal to 1 or m equal -1 would occur at a smaller distance away, because again, the whole interference pattern is caused when you are an integer number of wavelengths apart. And so the smaller wavelength means you wouldn't have to go as far. So they definitely overlap here in the center. Let me not get to part B yet. That's where it gets kind of hard. But this is kind of setting it up for part B. The first part, part A, is simply this. What is the distance between these two slits if you are told that the distance from the center to the first bright one is, and it varies from test sheet to test sheet. And again, does the tan one say 45 millimeters? Is that what the tan one says? All right, so those of you who've got the tan one, it says that distance is 45 millimeters. That's kind of how the numbers I worked out, so I assume that must be it. So if you remember this equation, this is kind of that first step, and hopefully the easy step was to say d sine theta equals to m lambda. Where it got a little bit harder here, meaning you couldn't just plug and chug in here, is you would have to know what wavelength to put and what integer to put here. Well, since it says the first bright one, then I'm looking at order 1. But also, it would have to be the shorter wavelength. And so you guys have different numbers, but that was a big step there. A big key is to realize which of these two to use and which integer to use. And so that's why I said the whole test actually is you can't just blindly plug and chug. There's an m there, but m could be any integer, right? And by the way, keep in mind it has to be an integer. That's going to come to play in number 5. Some of you were putting m equaling like 0.672, and I was like, where are these people coming up with m not being an integer? I mean, that was the condition of all of these. But anyways, we'll get to that one. But this has to be an integer, and it's got to be the first one here. So it's got to be an m equal to 1, and it's got to be the shortest one. Okay? Then sine theta can be approximated as tangent theta, which is the distance on the screen divided by the length. So this is A, find D. So 0.045, if I do it in meters, the length of the screen, I think in all cases was 75 centimeters, so 0.75. And then the wavelength, and of course depends which test you had, but the tan one here had a 440 nanometers for the shortest one there. And so putting that number in there, D comes out to be 7.33 times 10 to the minus 6 meters. So 7 microns, and the other tests were somewhere around that number, but definitely differ in the sense that their wavelength, the short wavelength, was different. So like I said, this is A, where d sine theta is the equation, and then there's a little bit of thought on what integer to use and what wavelength to use. Gets a little more interesting here in B, and maybe you can see the pattern developing. See how they overlap here, but not here, not here. As we go down, I think you can begin to see how the separation gets bigger and bigger, and eventually what's going to end up happening, and I'll just draw it at m equal to 3 here, and the blue one might be right here, m equal 4, and so this order of the blue one is getting a little bit closer. We're going to get overlap where the higher order of the shorter wavelength is going to be at the same screen position as a lower order of the longer wavelength. And so it's not really there yet in this picture, and that's where our math comes into play here. If we remember then, we have d sine theta equals an integer for, say, the first wavelength, but also d sine theta equals some integer times the wavelength of the second one. Then you begin to realize that if they're going to overlap, they got to be at the same angle. So m1 lambda 1 has to be m2 lambda 2. That's the key here. And so m1 over m2 would have to be lambda 2 over lambda 1. In other words, the ratio of the wavelengths would have to be the same as the ratio of the integers for where they overlapped. And so each test is a little different there, but the tan one had a 440 nanometers for the short one, and 550 for the longer one, which after we reduce a little bit, I'll divide by 10, then I'll divide by 11, and I get 4 over 5. And so that tells me that the fourth order of the red one overlaps with the fifth order of the blue one. And so the fourth and the fifth overlap, or what some of you did, you just started calculating a table and figured out where the heck do they overlap. And a good thing it wasn't 100 or something. It showed up after 4 or 5 of them. So you could write this as 4 times the longer wavelength, which is 550, or you could write this as 5 times the shorter wavelength. Either way, that should equal to d sine theta, where we just got d, and then we could replace sine theta with y over L. And so whichever order you pick there was going to give you your y value. And again, for the tan one, they overlap at the 4 and the 5. The other ones are some other ratio of wavelengths. But this comes out to be 22.5 centimeters down on the screen here. So you've got kind of the next picture there. All right, well, back to the gold one here. How about number 4? Number 4, this is light coming into a single slit. Okay? And again, like a lot of these, hopefully A is reasonably straightforward. But then got a little complicated as we added more to it here in B. But in number 4, you have just a single opening. And there is some wavelength. Now for the gold one, it was the rounded sodium color, the 589 rounded to 590. So this is a yellow light that we've used many times in the lab coming into this single slit. And they give you the width of it, and here was the idea. The idea was to remember from chapter 38 that when the light comes in here, the intensity pattern had a set of fringes. It followed a sinc function that we talked about here, but that wasn't really needed for this problem, is we just needed to realize where the dark spots were, and that would be then the size of our central bright fringe. And we learned that A sine theta equals an integer number of wavelengths is the place where you get your dark spots. Noting that it looked a lot like the double slit, but this is where the equation we got the bright spots. And so that was my warning in class that, hey, be careful not to mix those. And most of you didn't, but a few of you were still labeling this as representing bright spots, and so you took an integer plus a half to do dark spots, and then that's not the case. This is the equation of where you will get dark spots for the single slit. This is the equation of where you will get bright spots, okay, for the double slit. All right, but back to this one here. And so if we do that same approximation that we've done many times, and we look at order m equaling 1, this should give us the distance from the center. So it gives us half the distance. So that would be my angle. So in the case of the gold one, the opening was 1/10 of a millimeter. The distance to the screen was 1.4 meters. The wavelength was 590 nanometers. And so as I put these numbers in, at least for the gold one here, I get a distance of 0.00826 meters. So about 8 millimeters. Of course, to get the size, I need to double that. And so 16.5 millimeters was the answer to A, is how big is the bright one. Okay. And that, again, was probably the easier part of the problem compared to now. And now is we put a lens in between here. And so now our picture that had this opening and had this screen, now we put in this concave lens. And if I was just drawing a picture here, I know that this lens makes the light diverge. So it was already diverging a little bit as it came out of this hole. That was the whole point of our single slit diffraction. The diffraction is that it spreads out. This is only going to make it spread out more. So if it was about here, and so the light was heading something like that, when it hits this, it's only going to spread out more. So I guess my drawing looks something like this. But what I guess I want to do then is really ask this question. What does the screen see, right? Back here. What does the screen see? Well, the screen sees an opening 1.4 meters away. The opening being 1/10 of a millimeter. So what I can do, and this was the point of it, was to put last chapter together with this chapter and to say, and maybe I'll change colors for effect, but what's going to happen is as the light goes through this lens, so if this is the object for this lens, an image will form. And we have yet to do that calculation. But the image that will be formed, as we'll see, will be something like that. That will be the image. And that image will then have a smaller opening. But the point is, the screen will see that. So the object through the lens becomes an image. This image becomes the object for the next optical piece. That's the key. Now, please don't mix that with some of your calculations. Some of you answered, and I think you're probably questioning, what did I do wrong? And what you did wrong is, instead of putting the lens between them, you made it sound like you were going to put the lens and look at the screen through the lens. And so you had the light reflecting off the screen going through the lens and asking yourself, what is the image that I would see if the screen is the object for that lens? Do you see that difference? Very important difference of how the light is being controlled. And in this case, the light goes through the lens and onto the screen, as opposed to the light continues to the screen. As it comes off the screen, I hold up a lens and the light goes through the lens and I see my magnification. So some of you treated this as the object for that lens, like you were looking at the screen here. And then that's why I specifically use the words, how big is it on the screen here, not with the idea that hopefully you wouldn't be saying, well, what is the image I would see if I looked through it again? Well, anyways, if I run through the numbers then I would have 1 over P plus 1 over Q is equal to 1 over F. So in all the cases, the lens is placed right in the middle. Now, the distance is a little different, but right in the middle for this gold one would be 0.7. The focal length is given to you, but notice it does say the magnitude of the focal length is 50. So that, again, I need to put in the negative, keeping track of my sign. And make sure my units match. So if I'm going to do this in meters, I better do that in meters. Or I can switch that to centimeters and that to centimeters, whatever you want to do here. But it looks like I did it in meters. And so if I do that, I get a negative 0.292. And so that's why I was saying this math will show me where the image is. So this is where the image is. It is on this side of the lens, negative. It is not as far as this, 0.7. It's roughly a 0.3. And so there is the location of the image. And the magnification, which is negative Q over P, would be a 0.416666 repeating. And so what I would call the new opening, that is the size of the slit as seen by the screen. Because remember, this lens not only changes the position of it, but it changes the size. There's a magnification in it. And so not only do I need to know where the slit is in location to the screen as viewed by the screen after the light goes through this lens, but I also need to know how big is that opening. So I would multiply it by that, and the 0.4166 repeating times the 1/10 of a millimeter gives me my 0.0416 for the size of my opening. And that, like I said, is getting hard. And it was supposed to be. It's 4B. So if you saw that, great. Not supposed to be as hard as 5B. That's still to come. That was supposed to be a hard one. And I think it was. That was the one that tripped people up the most. But now I can finish the problem by really going back to the same thing. So now I'll just plug and chug into here, knowing that I have a different A and a different distance to the screen. So A sine theta equals m lambda, A and the L, and I'll put a little prime to indicate this is what I would see. So this becomes 0.0416 times 10 to the minus 3, at least for the gold sheet. The Y is what I'd like to find. The L is the 0.7 in terms of meters. My M is an integer 1, and the wavelength didn't change, so that's the same number there. And so after a little math, I get 0.014 meters for Y. If I then double that, it's a 28. So it's about a 28 millimeters. So it is bigger as compared to the 16 I got before.
Wouldn't L prime be 0.7 plus 0.2?
Oh, shoot. Thank you. Yes, it would be. And I hope I did that on the solutions. Yeah, I did. Okay, yeah. Good. Yeah, the L has to be that, which is the 0.7 plus the 0.292. Yeah, definitely. And that is the number you will get. Yeah. All right, well, if that made sense to you, on to the granddaddy. Oh, blue test. All right, so we'll switch to the blue test for the numbers. And so this one is about our thin films and our interference. And again, hopefully the first part is pretty straightforward. You did a homework on it. I did it in class. I had that sodium light and the video the video screen up there, and we looked at the sodium light and we looked at the wedge shape. And so this one says that you are going to shine some light, and at least on the blue one, it's light coming from our helium lamp, and it's that blue one there, so it's the 489 nanometers. The wedge is kind of exaggerated here. Here's this tube we want. The glass sheet that it is sitting on looks, something like this. And don't forget that the interference happens within the thin area, right? That's what we call this thin film interference. So we don't have to worry about how thick the glass piece is, and nowhere in here does it say anything about that. We have to be close, remember, for interference to occur. That was kind of our argument. If you remember those Newton rings ones I passed around in class, I mean, we ignored the thickness of the glass. It was just the stuff in between. Just like you've probably never seen the interference, on a window. It's just too thick. And we have to have a thickness or an overlap with near the wavelength of light here. And so that's why it only works for thin films. That's why it's called for thin films only. Keep that in mind, especially as the problem gets more harder in part B there, right? And so this first part is just looking at this interference pattern. So let's run through this. We can look at some thickness. Let's just look at it anywhere, thickness T. But the idea was that light comes down and reflects off of here, and it continues on down and reflects off of there, saying that the extra distance the second beam travels is 2t. And as we worked out in class, if that is an integer number of wavelengths, we would expect constructive interference if there was nothing else going on. But there is something else going on. There can be phase shifts. And so we got to analyze that a little bit. Let's see, this one is reflecting from in the glass to the air. No phase shift. But this one is reflecting as it goes from air into the glass. I'll circle it to indicate that one does undergo a phase shift. So where I expected this to be constructive interference, one changes and the other doesn't. So now this is destructive interference. This is minimums, or this is dark spots on reflection. And so that's how I would kind of start my analysis and say, okay, What's the path length? I would at first expect constructive, but then I'd ask about the phase. And so this is my equation for dark on reflection. Now, reading this question, that's perfect. That's what I want, at least in part A. Because part A says that I do see some dark fringes. On the blue sheet, it says 39 dark fringes. The other ones have a different number here, but 39 dark fringes here. All right? So this would be the equation I would want to use. And that's the question. I want to find the thickness. So the thickness would be way over here at that last dark fringe. And so I need to solve for T. Now, the two things to be careful about here is, first of all, our integer. Now, it does have to be an integer. It's not 1 this time. It's not even 39. Even though it says 39 dark fringes. What is it? 38. Why 1 less? Right, because this is true for m equaling 0, 1, 2, 3, 4. And by the time I get to 39 dark fringes, I'm at the number 38. All right, so make sure you put a 38 there for your integer m. And then your wavelength, now again, for the blue one, it is 439 nanometers. You guys would have a different number, yeah.
So I understand why it's 1 less, but in reality, wouldn't you say that the first dark fringe starts at the corner where there is no thickness, therefore it's not really a dark fringe, it's close to a dark fringe?
But why wouldn't I call it a dark fringe?
Because it's not really there, that's where the corner meets.
Oh, it's there.
It approaches a dark fringe.
Oh, no. Well, okay, remember it's going into darkness. So what you would see, if you were to look straight down, there would be a width to your dark fringe. And you would see half. How's that? You would count it. Okay. I would count it. I meant for you to count it. And I think the homework had one like this where you actually count it.
We all got that. But
Yeah.
It's not really a dark fringe. It's close.
Now you're down to semantics. I would call it half of a dark fringe. How's that? Yeah. But if I was just eyeballing it out, I would see 1, and then I'd see a second, and then I would see a third. But I would probably see that right away and say, okay, there's where the corner touches, and that's 1. Anyways, I would count it. And now we're down to semantics. But like I said, I think the homework had you do that. And you guys must have. Most of you put 38. Yeah. The other careful thing is, what about n? Yeah, see, n is where the interference is taking place, right? What's the extra distance? And the extra distance is in this wedge. So the wedge is filled with air. It even says an air-filled wedge there. So make sure you use 1 there. There was a couple of you who put 1.5. And I know what you were thinking. You were thinking about the glass. But that's not where the interference is going on. The interference is going on, or the extra path difference, I should say, is going on here inside the wedge, which is then filled with air. And so again, that's the beginning part, which is, the easier part of this. But you still got to get that integer, and you still got to get that index right. I gave you the wavelength, and you got to figure out which of the equations is the right one. But once you get all that, for this, I come up with 8,341 nanometers, or about 8.34 times 10 to the minus 6 meters for the thickness. So about 8 microns is the thickness of this small tube. And as you can see, a great experimental tool for getting the size. And the reason I put it up there, when you saw me do it in class, I just plopped it on there. And I knew there would be dust particles about that size. And so it was really easy for me to get it in class. I just put it on there, and sure enough, we had this kind of these stripes in there. Well, here's where it gets a little bit harder in B, because we changed the experiment, and what ends up happening is we have another thin film to worry about, and that's the one going down here at the bottom. All right, so let me leave this alone for a moment, but this is true for this wedge shape. Let's talk about this one for a moment. If light was coming down and reflected off, and then went down and reflected off there, using the same logic, I would say 2t equaling an integer number of wavelengths in that film, I would expect constructive interference if nothing else occurred. But there is other things occurring here. Are there any phase shifts going on here? Well, here's the glass, 1.5, and the thin film is 1.6. So there is a phase change right there, but not here as it comes out into the air. So this equation, which I would have thought of as being bright, is now dark upon reflections. And that's really the same logic we got here. Okay. But that also means the reverse. That is, if it's dark on reflections, that means this same idea is bright on transmission. Because if the light's not being reflected, it must be being transmitted. Yeah.
Going back to the first piece,
Oh, yeah?
I have to take into account when it's going from air to glass, that phase change.
Air.
Before any of that happens, above that piece of glass.
Oh, above it, it's going through it. There's never a phase change on transmission.
Oh, okay.
Yeah. So, only on reflection do I get any, possibility of a phase change. All right. Now, this would give me, this equation would represent bright on transmitting. And this is really the key to the problem. This is what makes the problem hard. There was nothing saying about this equation because the problem had you illuminating white light from above. And that means you are going to get all kinds of bright, dark fringes in the reds, the greens, the blues, the yellows. You're going to have every piece of constructive and destructive interference going on, except not all of that gets through the other side to be observed. And that's really the key. So if you missed that, that's what I wanted pointed out. The key is right here. What actually comes through this one? White light is going on in here. But the only ones we care about are the ones that actually get through this. So knowing that, and coming over to this equation, as applied to this bottom film then acts like a filter. It's the whole reason we don't need to shine a certain color of wavelengths. This filter will select them. What colors or what wavelength will it select? Well, let's solve this equation. Let's write it as 2nt over m is equal to our wavelength. So it would be 2 times 1.6 times the thickness. Now, you all have a different thickness, but for this blue one, it was 136 nanometers thick, and then I can divide by my integer. And my integer would give me the wavelength. And so I could be dividing by a 1, I could be dividing by a 2, I could be dividing by a 3, by a 4, ... We can get in a debate about 0. Let's not. But this would be all the different wavelengths that would come through. And if you start making a list of these, at least on the blue ones, I'll just divide by 1 the first time. And for the 1, it comes out to be 435 nanometers. In fact, I'll just put an M over here. So across the top, it's 435 nanometers divided by 1. Well, that would be one color that comes through. Divided by 2, that would be another color, but that wouldn't be visible. Divide by 3, well, that would come through, but that's not visible to the human eye either. 4, 5, 6, 7, so all those other ones are wasted thoughts. This is the only one that's going to come through that is going to be observable by the person down below. And of course, the gold one and the tan one has slightly different numbers, but the same idea. There will be only one in the visible range. And so the key here is to realize that for this scenario, m is equal to 1. It's also equal to other integers. In fact, it's equal to all the integers, but you need to realize that you wouldn't see all those. Okay? And some of you were putting some big numbers in here. I didn't quite figure that out, like 28 or 29 and 30, and I was like, wow. And got really small wavelengths, like 28 nanometers, and I was kind of thrown for a loop why you would pick that one. But anyways, that was Oh, I know why you're picking it. That's right, because you were counting these. Yeah, and you were applying that integer to this one. Yeah, that's right. All right, so don't confuse that, right? Real easy to do. We got two different films here. But in this film, the m is equal to 1, all right? Later on, m is going to be a different number when I come back and do the calculation for this one. But like I said, that is the first and important calculation. What wavelengths do I care about? And so, like I said, the white light was the clue that all of the colors are coming in, but it's this bottom one that's the clue that I don't care about all of them. I care about just one of them. Unfortunately, it was just one of them and not a bunch of them. So once you figured that out, now you can come back over to here and say, all right, if my wavelengths are of this value, see if I said that right. The ones that come through are of this value. Then, as I come back and apply my thin film again, T equals, and I guess I'll jump back over to here, because remember, this is the one we got in part A. This was the minimum on reflection. So it's also the maximum on transmission, right? So I'm going to still apply that equation. It would be m lambda over 2n. And what was nice about this whole discussion here is I now know what wavelength to work with. And that's why it was a hard problem, figuring out what wavelength do I use. It says white light. Doesn't white light have all the wavelengths? Yeah. And that bottom filter selected it there. All right. Another thing is to realize that I am looking at an interference pattern that is going on in here, although it gets transmitted through here. So don't confuse our ends, right? Now notice I used a 1.6 here because this was the interference in the bottom film. So the color that we're interested in is this one as it interferes in the wedge shape. And then of course we're back to our integer again, and we're trying to find its thickness, and so there's going to be, as viewed from down here, bright, 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 bright. Because remember, this dark one was dark on reflection. So when you're standing on this side looking up, this is going to be bright, 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 bright. And in this case, they say, the blue one says there's 27 bright ones. And for the same thing that we said before, I would put the number 26 there for the integer m, and so there's a 26. And when you do all that, you get a 5.65 times 10 to the minus 6 meters for that one. And if you got that one right, you should lift up your right hand, put it over your left shoulder, pat your back twice here, because that was a big step and a big connection here. All right. Well, oops, I spent a little more time there than I guess I wanted to. I always do. I get all excited about, oh no, you see this. But I'll jump back into the relativity then if there's no other questions. If you have some other questions, that's fine too, yeah?
So why isn't it that a thick piece of glass wouldn't have interference?
Oh.
At like M200?
Yeah, okay. So this first beam comes in and reflects. If it is really thick, it takes a while for this to come back. Okay?
Time? It takes a long time?
Time-wise. Okay? Now, the reason I say that is there is a little subtlety that I don't think we quite addressed in this class, but remember, when a light wave comes to you, it looks like this because it was light given off by an atom, but it only has a certain length to it. The next piece of light comes from another atom. So there's only what we call a coherence for so long. So if it goes down to here and back, and the light is coming from a different atom, then there's not a pattern between them anymore. They're not coming. There's not a coherence, is what we like to say, from the two. Yeah, and so if this is more than the coherence length or half the coherence length, then you're not going to see it. Yeah, so the thick ones we won't see. Plus, of course, you got to have these surfaces smooth to a fraction of a wavelength, and regular window glass doesn't usually have that, although that imperfection can show up nicely in, like when I passed out the Newton's rings, you could see the imperfections of the glass, and that was the whole point there. Yeah.
Do we know the approximate thickness that effect starts to have? Like how many M's about can you get?
Yeah. Well, no, it's not a set number. The coherence length would depend on the quality of that light beam. So a laser beam, this could be enormously long, and you could get the interference on something as thick as a glass window. But regular, ordinary light just coming from an incandescent bulb that you heat up, it's pretty small, and I don't recall what the number is, but you're not going to, because I don't know what that one comes out to be. But it depends on the quality of that source of light, obviously. And lasers are designed to have a long coherent length, so this will happen. As an application of that, it is nice to get that interference from a laser beam. I should, in terms of technology, and you were in the Air Force, I would assume the Air Force has it, but I know the CIA has it. It's actually kind of nice to be off at a distance, and if there's a window in a building, if you shine the laser beam on it and then get it back, as the glass vibrates, you will get an interference pattern on your detector and be a long-range Michelson interferometer. Now, the reason I say that is because then if there is something going on in that room and you want to know the conversation, the sound waves in those rooms are vibrating the windows at that. So from a mile out, I should be able to pick up that conversation through my interference pattern. So I don't have to get that close to spy on, would-be terrorists, type thing. And so it's a really nice application of interferometer. Yeah, well, hopefully no educated person ever gets too paranoid, because then, I mean, the bomb they built in Boston was child's play to what you could really build if you wanted to. Fortunately, most people don't want to. Yeah, what?
I said if you're a chemist, you could break bad. That show. Get it?
Breaking what?
Breaking Bad.
Breaking Bad. Okay. Sorry. Okay, so here's the game plan. Now we're done with that test. We're on to our last unit. As you know, we already started one unit. I showed you some really weird things that you hopefully are beginning to process and probably didn't give it too much thought that day, but now that you've took the test, hopefully I've been re-looking at that. And so I'll just summarize what we did and continue on here. But here's my game plan. We just have a few days left here. We've got today's lecture, the rest of it, 1 hour. We've got Thursday's lecture. We've got Tuesday's lecture. And that's it. Because then the Thursday after that, we'll just do the other half test. So we'll just have 3 questions on however far we get into our modern physics. And I would project that we would probably finish this 39, finish 40. It's kind of short, and I really hope so. And then we'll jump into 41 or 42. There's just some things that I think maybe might be a little more important that I show you. And again, all of this is, as it says, an introduction to modern physics, to show you the world beyond Newton, to show you physics in the 20th century, let alone the 21st century, but to really set the stage for those of you who may end up in engineering and science on a small scale or a fast scale, which is becoming more and more the realm of the future. And so I actually think engineering classes and technology probably needs to change, and more of the science of the small needs to come into that, because we're now at the point where we actually build nanotubes and we build nanotechnology. And so really kind of this last decade has been the time where it's not just the scientists, now the engineers need to understand the quantum mechanics. Yeah.
Are we going to have a review on Sunday?
Probably. I mean, I talked to John. That's what he's done. It would be this Sunday, wouldn't it? Wow. So short. Yeah, so I need to mention that to him. Yeah. Oh, Mother's Day. No, you got to see your mom. You can, maybe you can float Mother's Day.
I read in the news that the government declared that they've been running a quantum security intranet across the country for 2 years successfully.
Oh yeah, quantum encryption has. Yes.
They just made it public knowledge. This is the first time it's been.
Okay, they may publicly announce it, but everybody knows they're doing quantum encryption. I mean, that's pretty obvious. Yeah, the quantum encryption has been done. Quantum computing has not. Don't. Hopefully, you're not mixing the two.
You mean quantum teleportation?
No. When you encrypt the data.
No, I'm serious.
No, when you.
With the changing where you have the two. The molecules that are connected and
Yeah, entangled.
That's not what they're doing.
that's not what they're doing. That's what when I'm saying
No.
teleportation, that's what I'm referring to, not like
No. Quantum encryption is a very powerful encryption tool that without getting into the quantum mechanics yet, maybe we can touch on it when we get there, will allow you to easily tell if somebody had intercepted the data along the way in any shape or form. And that's the amazing part of quantum mechanics here. In fact, we're getting a little bit ahead of myself, but I'm kind of hoping to finish up this chapter. I don't know if it's going to happen today, probably not. But I brought this because it's one of my favorite covers. It goes back 2 years ago, Scientific America, but it's got this human, and it's quantized, if you will, and it says living in the quantum world. But I just love the subtitle to the article. It says, small-scale physics has a spooky power over the world behind us. And so as you saw weird things at close to the speed of light, I'll call them spooky now, you are going to see spooky things or weird things when we get small. And that's one of the things that it's just different. And different means we can do other things than we're used to. And fortunately, there's more things we can do. So the technology and the things we could and couldn't do, the principles that are applied for the large scale changes as we get to the small scale. And there's things that you would have never imagined possible and people haven't yet imagined. And that's where you guys are in a great place to start your career, because you're going to do things and the computers are going to do things that you're going to go, what? How could it possibly do this? I mean, especially on the quantum world and the quantum data storing. I mean, you're talking about, taking 1 cubic centimeter and you could store all the information in the world in that 1 cubic centimeter if you had a quantum storage system. That is an amazing possibility that has yet to be achieved. Anyways, but wasn't going into quantum mechanics yet. That's coming. All right, so what did we do last time? Well, we talked about special relativity. And in special relativity, we noticed one thing. And one thing only. Unfortunately, it's the one thing that affects everything else. We noticed. And we started that whole discussion. I know this goes back a way, so maybe it's worth taking a little more time to summarize. But we started with an electron, and we made it move faster and faster and faster and faster and faster. And one of the first things was noticed is it did not go faster than the speed of light. There was something about the speed of light. And it was Einstein who put that together, and I started our whole conversation with this, that if you took an object like a baseball and it had a horizontal speed and it had a vertical speed, to get its total speed, we applied Pythagorean's theorem. And that's what we had done since Newton's time. And that's what we did since I started with you guys way back in Physics 121. And I started that lecture by asking you, what was the justification for that? And in case you missed it, the justification was that the time was the same for each observer. Now, of course, what that means then is if I am in a train with a flashlight and I turn on the flashlight, if I see the beam go up at the speed of light, if the time recorded by me is the same as the time recorded by you, then you would see that beam of light going faster than the speed of light. You would have the vertical speed, the speed of light. Then you would take the speed of the train and you would get something greater than the speed of light. And what Einstein was trying to show is that it is possible for each observer to see the beam go at the speed of light, but only if the times aren't the same. And so that's where we started in this whole discussion, by saying that there could be different time frames, and so the time observed by you could be different than the time observed by me. In fact, that is the requirement if the speed of light is going to be the same for each observer. So we went through a bunch of math. And as we went through that math, we started with the assumption. We started with the assumption that the speed seen by you and the speed seen by me was the same. And of course, as I said, that would work out the same, but only if the times were different. And so our first conclusion was what we called a time dilation. That is, the time experienced by you and the time experienced by me were different. Which opened up a whole slew of problems from then on, because the first one is, how do we define the time? You know, when your instructor tells you you have 2 hours for a test, who's measuring the time? Because different people are going to see a different 2 hours. So I don't know if you've got a chance to do any of the homework, but some of you picked it up after the test. For the rest of you, it's up here. But one of the problems in chapter 39 is exactly that. That there is a class of students, and I can't remember if they're on the Earth or the spaceship, and the professor is on the opposite one, and the professor's going to give them an hour on the test or something, and the question is, how much time do the students get, or vice versa? And so you've got to figure out then which is the proper time, and then do a conversion to what I'll call the observed time. And so everybody's going to have a slightly different observed time. And so that whole consequence right here, that if the speed of the light is going to be the same for every observer, time cannot be. And if time can't be, then length can't be. And if length can't be, then momentum can't be or the same as we're used to. And energy can't be the same as it used to. And there's a lot of other things that can't be the same. And that's what the rest of this chapter is all about. So we did, second consequence was this length contraction. We went through a little train argument as the train was going down the tracks and said, all right, the length of the train would look a little bit smaller if it was in motion. And so we took what we called the proper length, because we have the same dilemma. That dilemma is, how long is the train? Well, who's looking at it? Is it the people on the spaceship, or the people on the Earth, or the people on the second spaceship? And so the length of something depends on what speed you are bothering to measure it. And so this whole idea of proper was to say, measure the time when there's no motion, measure the length when there is no motion. And that gives us something we can all agree on. We can all agree on what is the proper length of the train. We can all agree on what is the proper length or proper time on the clock. It may not be what you measure on your clock, because you're not at rest to your clock, or you're not at rest to the object, but those were the ones. And we finished, the last part of this is we finished with this whole idea that since time and for that matter space, have been affected, two events that occur at the same time from one reference point, unfortunately, do not appear at the same time from another reference point. And so, this brings us all the way back to our mechanics. How are we going to deal with velocities? How are we going to deal with momentum? How are we going to deal with forces? How are we going to deal with energy? Everything has been fouled up because of time. Time is totally different than what we've kind of assumed. The good news here, though, is the time does not change by much until you get more than the speed of light. So I want to keep emphasizing that everything we've done, don't forget it or throw it away or think it's useless. It is just incomplete. And what we're about to do next is something we would start to do as we got closer to the speed of light. So everything we have done is a good approximation. Kind of like sine theta equals theta. Good approximations. Really good approximations at low speeds. And I'm talking about low speeds, the speeds of, the fastest thing on Earth.
I think you mentioned
Oh, close to the speed of light. Yeah, I did. Not more than the speed of light. I didn't mean to say that. You're right. All right, so let's go back and reanalyze this. Let's do this problem. To help you understand this, let's look at what I will now call the old theory. The stuff we first learned. What we will call a Newtonian relativity. And so let's make sure we understand what we had been doing back in Physics 121 before we make it worse now. All right? Let's ask this question here. Let's take two reference frames again. You can see the relativity. I'm going to use you guys again. You are going to be in what I will call System S. Okay? And so you guys are in the classroom. I will be moving along in what I will call System S prime. So again, like we did a week ago, imagine this. You're standing on the side of the tracks. I'm in the train. I'm moving along in this train at some velocity v. Okay? So when you look at me, you say, hey, he's moving to the right with v. Of course, I would look at you and say you're moving this way with v, which if I paint this way, I'd say to the right also. Okay? And say, okay, you're moving my way with the speed of v. But let's say we each look at a bird. There's a bird off in the distance. There's that bird. Now, this bird is at some position, right? Now, this position would be measured by you, I'll call it xy, or it'll be measured by me, x prime, y prime. Now, in addition to having a position, that bird would be moving. So let's say the bird is headed off kind of like this. So you would say, okay, that bird has a speed. Now I want to make sure you get the notation straight here. Notice the S without a prime. Position without a prime. Seen by me, system with a prime. Coordinates with a prime. What's V again? Velocity of me relative to you. So what shall we call the bird? What shall the bird speed be labeled? And I want to emphasize, I don't want to use a V then. Okay? And so what speed is the bird? And of course you would see one, and I would see one. So I guess I'd call it a prime, you'd call it an unprime. But let's call it U and U prime. And so the U's are used for the speed of the object. The V is used for the speed of the reference frame. Did you catch that? Because I think that's really part of the hardest part of what we're about to do is the students really mix this up because it's relativity. And when you do relativity, what makes it hard is you got to ask who is looking at what. And so the prime and the unprime get to be a little more complicated here. Now again, hopefully keeping it simple, if you were to say that my position, my origin, was at the same point as you, your origin, when the clock started, then I would say that in later moments of time, I have moved forward, right? So in other words, look at this number carefully. This is saying that our two coordinate systems, our two origins line up at time equals to 0. Okay? Other than that, they don't line up. So here's your coordinate system. And I suppose you shouldn't be moving, but to keep it simple, I'll say you're not moving, and I am moving. And so right, time equals to 0. And then as time continues, I move ahead of you. Now the bird can be doing something else. If the bird is flying even faster than me, it would be moving further that way. If the bird is flying slower than me, or even towards me, then we would be cutting it, this distance here. So there's a lot of things the bird can be doing here. But I want to emphasize then, as I go to ask this question, how is x the distance you see the bird related to how I would see the bird? Well, let's take a moment in time. I would be right here, and I would count 1, 2, 3, 4, 5, 6, 7 tick marks, right? I would say the bird is that far away. But I would also say that I am this far away from you. So what distance do you see? Well, you see my distance. I mean, you see your distance that you see is the distance I see plus how far I'm away from you. Kind of make sense? Or the other way around. What distance do I see as measured from you? Well, you would count the number of tick marks, right? You would say tick marks, and then you would subtract this. Yes?
T prime.
Now, good. I'm glad you asked that. Because I'm going to say, again, here is what we're going to call our transformation. Okay, again, this is the old theory. Okay, and hopefully, like I said, this will help for the more complicated what we're going to do next here. But what I'm trying to get you to see here is if you were making the measurements, you would measure a distance x, right? Then you would measure a distance of my coordinate system, so you would measure a time. Now, maybe I should write it next that the time you observe and the time I observe are the same in the old theory.
This is the Galilean transformation.
And this has a fancy name called the Galilean transformation. Galileo was the first one to do this. He's asking this question. The same question I'm trying to ask is, if you wanted to know the speed of the bird, how could you figure out the speed of the bird that you would observe if you knew the speed I observed plus you knew the position? How could I go from one observer's point of view to the other point of view? Okay? And so again, the Galilean transformation is the simplest one. It assumed the times are the same. You can see how this is going to get more complicated in a second. This was the whole point I'm getting at. That little step, by assuming the times are the same, is wrong. And so I want to fix this old theory and get a better theory, what we will then call a Lorentz transformation. So Lorentz is going to go through this and fix the whole Galilean thing. Yeah?
So what's the difference between you and you, Brian? You as an observer by the standing.
Okay. So again, another reason I want to go through this old one is not so much to reteach you the old stuff, but it's really about notation. The u is the speed of the bird observed by S, the unprimed system. U prime is the speed of the bird observed by S prime system. Just like x and y are the coordinates of the bird as observed by the prime system. And x, y without a prime are the positions as observed by the S system. Yeah.
Is it fair to ask for what's moving?
No. No, as you'll see here in the transformation, then it comes out to be the same. We go from one system to another. So it's impossible to say which one's actually moving, other than to say they are moving relative to each other.
Could you explain one more time why the times aren't the same? The time frames you just say wouldn't be the same.
Okay, well, they are the same in the old theory. Before last Tuesday, the times were the same, and why they were the same was just an assumption. And it was Einstein who then said, if we assume that the times are the same, then the speed of light by different observers would have a different value. But that's not what seems to be happening in the experiment. So Einstein took the bold approach of saying, well, what if the speed of light was the same from each observer? Is that even possible? Does that even make sense? And when we wrote out the equations, and I don't have time to write them all out again here, but I'll just say go back and look at those. When you do assume that the speed of light is the same by both observers, you can show that the time then has to be different. And that's how we ended up with the time dilation, that the times would be different. So this was an assumption that was used by Galileo and Newton and everybody else until Einstein in 1905 here. And that's what we're going to change here in a few minutes. Yeah.
We couldn't say which one of those was moving, but we could say which one of them was moving more based on the time dilation, right?
Well, that's okay. Hold off on the time dilation, because right now there is no time dilation in this model, right? But I'll say yes to that. Make it short. Yeah, yeah. But going to this, then I would say the y observed in each coordinate system is the same if I'm only moving in the x direction. So the position of the bird up in my system and the position of the bird up is the same as yours. And it doesn't really show here because I didn't draw a three-dimensional, but coming out of the board would be the same thing. And so the only thing would be different would be a different x value. And what Galilean asked was this: how would I calculate the speed of the bird as viewed by you compared to me? See, I just did the first step. And the first step was, how do I get the position as viewed, well, if I viewed position in time, how does that relate to you? If you view position in time, how does that position appear to me? And so you would probably do something like this. You would say, u is dx dt. U prime would be dx prime dt prime. All right, so let's take a look at this. If I take this equation for x, which is right here, and I take the derivative of it with respect to time, what do I get? Well, I guess that gives the dx prime, and there's a plus or minus over there, plus a v dt prime over dt. And if you're willing to say dt prime and dt are the same, which they are in the old theory, they're not in the new one. This is what's going to really make it hard. But in the old one they are. I would get dx prime over dt plus v. I could even put a prime down there because the t and t prime are the same. And so this would be u prime plus v. And down here, if I did the same thing, I would get u minus a v. And I doubt if I've done anything that surprises you. I mean, think about this. What is this really saying? What speed do you see for the bird? is nothing more than the sum of my speed and the speed I see. In other words, if I'm cruising down in this train and I look ahead of me and I see that bird going away from me at 10 meters a second, and you look at the train and you say the train is 5 meters per second, what do you think the speed of the bird is? 15. 10 plus 5. Exactly, right? Nothing new. That's what we've been doing, right? If I looked at the vertical direction, oh, and I should have put, this is velocity in the x direction. If I look at the velocity in the y direction, I would get that. Or if I looked in the prime, I'd get that. Either way, that has the same value. So the motion in the vertical direction is unchanged. In other words, if I'm cruising along on the train and I say not only is the bird going 10 meters per second that way, but it's going 3 meters in that direction, you would say the same thing. You would say it's going 3 meters up. Again, that's not a surprise. What is a surprise is, what if, because of motion, time and length change? How are you going to figure out the speed of this bird? And that's the new stuff. Yeah?
I still can't see how x equals x prime plus b times t. So x prime is basically the initial position as observed by s prime, right?
So this whole distance is x. So where is the bird as seen by the unprimed? I claim x is equal to this distance, x prime, and this distance, vt. Right? And so there's my transformation. All right, now if that made any sense to you, and I'm hoping it did, let's just do it again. Same thing, nothing different, that's what I want to emphasize, other than there's going to be length contraction and time dilation. And now I can ask this question. If this bird was going at any speed, including speeds close to the speed of light, and this train was going any speed, including close to the speed of light, what would I get? You see, here's the problem. The problem that I have with this old one doesn't show up until I get going real fast. But when I get going real fast, let's say this. Let's say the train was already going 3/4 of the speed of light. And the bird is flying 3/4 of the speed of light. According to this equation, what would you see for the speed of that bird? You would say, well, okay, bird's going 3/4 of the speed of light, as seen from the person in the train. And then the train's going 3/4 of the speed of light. So the speed as seen by somebody who's outside of the train would be 3/4 plus 3/4, which is 1.5 times the speed of light. And if the world worked that way, it would be a lot easier. But that's not what happens. The object does not look like it's going 3/4 of the speed of light. In fact, as you'll see in a second, the object will still look like it's going less than the speed of light. So obviously this formula is wrong, which is obvious because we already did time dilation. And we need to go back and redo it. We need to get the right formula. However messy it will look, so be it. We got to get the right one. Yeah.
Would you even be able to see the bird?
Yeah, because it's not going the speed of light.
I mean, if in that scenario,
Oh.
the bird was going 1.5 speed, the light wouldn't hit the bird and bounce back.
Okay, fair enough. Fair enough. So, but let's say what we really should observe, okay? Because I do claim that there could be a scenario, now probably not with a bird or a train, but with other objects that are small enough, we could make one object go 3/4 the speed of light. And then off of that object, shoot another one at 3/4 the speed of light. And then ask, what would you see for that speed? And what you'll see is it will be close to the speed of light, but will never be over the speed of light. As you'll see, the equations won't allow it. No matter what the speed tends to be here. So let's look at this same one. Let's then put what I will call the new theory. Let's look at a more complete picture and get away from away from a Newtonian point of view and go to an Einsteinian point of view and do what you pointed out. This is a Lorentz transformation. So let's do the same thing. And I'll probably have to save a little bit of time, so I'll cheat the math a little bit.
So those are representing moving, like S prime is moving and S is not, right?
But let's do the same thing. So I've got one system, and let me not say whether it's moving or not. If it makes it easier, I'll say it's not moving. But what I do know is I've got a second one that is moving relative to that one. Okay? And so, if you were looking at me, you would say, how far am I from you? Well, you would say VT, right? Again, V being the velocity of my train relative to you, and T being the time that you would measure. But on the other hand, how would I say how far you are from me? Well, I guess I would see you coming towards me at V. But I would measure some other time. Right? And so I would say your is V times T prime. And so my T and T prime aren't the same anymore. And unfortunately, it's going to make my math kind of hairy, which is going to make all my math a bit hairy. Which again is why I don't really want to mess with this math unless I get close to the speed of light. And then I'll be forced to. Okay, now let's go back to the bird again. So here's the bird. The bird is moving at some speed u as observed by you. But it's moving at some speed u prime as observed by me. Its position is xy as observed by you, but I would call it x prime and y prime as observed by me. And so if I were doing the same thing, I might ask this question. What is the position of x as measured by you if we know the stuff measured by me? Well, I guess it would still be an x prime because I would count over this. Right? I would count over a certain number of tick marks and I'd call that x prime. Oh, plus what I have to add to that is all the tick marks that go back to you. So just like we did here, I would have to add a VT prime. The only thing that is different is that when I look at your scale has been shrunk. And so I'm going to get more tick marks. I'm going to get more tick marks by a factor of gamma. So I would have thought it would have been this, but as I look at your scale, I'm going, well, your scale's smaller. So this was supposed to be 7, but now it's 14 because your scale's smaller. And so there's my transformation. Yeah.
So when the size changed, does the density or mass change?
Yeah. I'll say yeah to that. Yeah. And then the other way around is the same thing. X prime. Right? Same kind of logic here. Same kind of logic here is I would say this is an x minus a vt, but when you look at my scale, you're going to say, no, your scale's all messed up. Your scale has shrunk a little bit. So the tick marks are bigger by a factor of gamma. Because you would have said, okay, measure this whole thing, subtract this is what you should see, except they change by a factor of gamma. Yeah. Why does the scale change? Ooh. All right, back to length contraction. I've erased it. But L equals, does this look familiar? Do you remember when we derived that? Okay, so this is saying that if I had a scale that was 1 meter long, but then I look at that 1 meter scale in a frame that's moving, it's going to be shrunken by this much. And so all the lengths that, as I try to look from one observer to another, keep changing by this factor of gamma. And time does too, so I've got another issue to worry about. Oh, they would be the same gammas because the v, the speed that I see, or you see me moving, is the same speed that you see me coming back. And that was the nice thing then about something that's consistent in all of this. Our time is not consistent, our length is not consistent, but our speeds are. And so to be quite honest, I can't help but wonder if we do our science wrong. We should not have a grid based upon position and time. Those all change. It's speeds that don't change. So in fact, there's a good book written called The End of Time. And it's not like a doomsday end of the world. It's a science book on saying we keep measuring things in time, and that's a mistake. We as humans invented time mistakenly. It doesn't help us. Or it does yeah, it does, but But time is apparently, interesting enough, of all the great science we know, time is probably the least thing we understand. We're constantly asking, is time travel possible? Can time go backwards? We don't know. We know very little about time, as simple as it may seem. We just don't know much about time. Yeah.
So which one is the proper time in this case?
Well, I would say neither, depending on what your object is. If your object is the bird, I would have to have no motion. The bird is moving relative to each of these. So the person who's going to measure proper time is the person who's riding on the back of the bird. There's no motion to the bird. They're sitting on the back, flying along, stopping. That's where the proper time is going to be. Okay? All right. Now, if that was okay with you, at least this isn't so bad. Because remember, we said things shrunk only in the direction they were moving. All right, so if I'm moving relative to you on the x-axis, as I look back on your grid and you look on my grid, in the vertical one, we agree. There is no gamma. Oh, that was fortunate. All right.
That works for every case, right? Because even in the length contraction?
This one?
The length contraction?
Oh, here, yeah.
Yeah, that works in the train too, because if we're moving at a big velocity, it's almost equal to zero, right?
Yes, yes. So yes, and all of this brings up a good question. If the length really shrinks, how come I've never noticed it before? Right? I mean, I've been driving a car and I have never seen the car next to me get smaller as I drive faster, right? But the truth is, I just haven't noticed it because, as you're pointing out, V squared over C is a small number, right? Unless, of course, you get close to the speed of light. And when I say close, I mean 10% the speed of light, which doesn't really sound that close. It's only 10% the speed of light. But at 10%, you square it, that's 100th. And so even at 10%, I'm only going 1 minus 100th. And that's just barely noticeable at that. So that's why we like to say, hey, you're not even going to notice this till you get 10% the speed of light. So yes, it is happening around you, but you don't notice all of this. That's why we're adding to the science that we've learned. Yeah?
What's that density thing earlier? What for the person going the speed, density would change the length was changing?
Yeah, so the density is going to change.
It would change?
Yeah.
I thought the length, if you're the person going like this stays the same only for the person who's watching.
Okay, right. So if I'm in the train, moving along, the train doesn't change its size, and the density of the train doesn't change for me moving along. You observe the train, watching it compress, and saying the train is more compact, more dense.
It's also relative.
Oh, yeah. Yes, that's the problem. Once you mess with time, everything has changed. Density has changed. Kinetic energy is going to change. Total energy is going to change. Interesting enough, mass is going to become a form of energy. Momentum is going to change. The equation for just calculating the speed of the bird, I haven't even got there yet, is going to change. Everything is going to change.
Wait, so it's possible to compress something by simply launching near the speed of light, and then at the other end you see it?
Yes. All right, so in the interest of time, I will skip some algebra here. Yes?
So we're assuming the bird's only moving in the x direction in this.
Not the bird. No, I'm not assuming the bird is. See, that's why I did a velocity in the x and a velocity in the y. So the bird can have a motion x and y. It's me, the observer, is only moving in the x direction to you. Yes. Yeah. But you're getting this, the complexity. Which speed are we talking about? Are we talking about the observer, the first observer, the second observer, the bird, the x component of the bird, or the y component of the bird? And you'll have your chance to struggle with this, yeah. The bird is moving, okay? And what I'm trying to get at is what would be the new silly equation, all right? And so now that I've kind of running low on time, I'll save some algebra by saying this. What would be the transformation of one time as seen by the other system? And probably the best way to do that is to leave the algebra for you. And I'll put it into there. But if you take that x value there, you put it into there, you rearrange it and solve for time, you will get gamma t prime plus v c squared x prime. If you do it the other way around, and you take x prime and you put it into there, you will get something very similar. But very complex. And like I said, in the interest of saving maybe a little bit of time in terms of the algebra, because I feel like I better get to the results here, this is the time as measured by u. So in other words, if I am watching something at a distance x prime, that's what I would say. I'd say, where is the position of the bird? X prime. How much time took place? Maybe this was one flap of the wing. Okay? I would then say this, maybe that was a bad example. That would be a change in time, t1 minus t2. So, okay, so I look at my clock and I go, okay, the time is 12 o'clock and the bird is 5 meters from me. What time do you see? And it won't be 12 o'clock. It'll change by what's the position of the bird and how fast am I moving. And likewise, the other way around. If you look at your clock and you say, oh, it's 12 o'clock, and you look at the position of the bird, and the bird is, say, 18 meters, you could calculate what time I would see on my clock. And it won't be the same you see on your clock. But that's exactly what I was after. What time would be on my clock compared to what time would be on your clock? All depends on what position and what time and how they're connected to. Certainly much harder than before. Yeah. So gamma, as in all cases, gamma was that 1 over the square root of 1 minus v squared over c squared. And again, notice it's a v, not a u. Because the v is the speed as, as it changes because I am moving relative to you. Well, now, I think I'm finally getting to the point I wanted you to see, and it's got multiple parts, is how am I going to get now the speed of the bird in one reference frame as seen by another. So if I call u prime in the x direction, how the position changes as seen by me divided by time as seen by me, I could take the derivative of this and get gamma dx minus u dt as I took the derivative of this one.
It's V, right?
Is that B or G?
Where?
Right there.
Minus V dt.
That one right there, yeah. Is that V or?
Well, you said minus U.
Oh, I meant v. Yeah. So I'm taking the derivative of this one. So I got a dx, I got a minus v, and I got a dt. And again, I wanted to emphasize, that's why I went through the old one. The old one, I'm doing the same math, or the same logic. It's just the equations are much more complicated. And the result's going to be much more complicated here. Let me take the derivative of this one down here. That would be a gamma, and then I would have a dt, then I would have a minus v dx c squared down below. And maybe to make it worthy of velocities, I will multiply 1 over dt in the numerator and in the denominator, because in the numerator here, I would get the I would get the u in the x direction minus the v. In the denominator, I would get 1 minus, and this is the surprising piece, a v, a u, and a c squared. And so notice, in the old theory, we just said add them together, right? And that's what we often did. And the example I gave you is if the bird was going at 10 meters per second and the train was going at 5, you gave me 15. So let's do it again. But let's use the correct formula this time. So, oh, did I mess up my sign? I did this one first, didn't I? Sorry. I guess I just did that one, didn't I? I did the u prime. Let's do the u without the prime. And so this would be a dx dt. And so this would be a gamma x plus v dt. And dt would be down here. So this would be gamma dt plus vu, well, sorry, I haven't got to dx c squared. These would be primes. Dx. So this would be a prime, a prime, a prime, a prime. And the nice thing about this is I would get this ux prime plus v, and then I would get a 1 plus, here's the v, here's the u prime, and here's the c squared. So the point I hopefully was trying to get for the last few moments here was the new formula is a bit more complicated, right? Whereas the old one, what I did is I said, let's just add them together. Let's try it again. Let's take that bird that as seen by me is going 10. The train I am on is going 5. I'll divide it by 1 plus, what do I get down here? Well, the train is going 5. The bird 10. What's this? 3 times 10 to the 8th squared. Now that number is maybe not quite 0. Pretty small. If I put it in my calculator, I don't think it'll even show up because isn't it 16 decimals over? So my calculator will still just show a 1. So if I put all this in my calculator, I still get 15. And so you can see that unless you're talking about large speeds, this bottom part is not really important, which is why we have taught you for the last 2.5 semesters or 2 3/4 of a semester to ignore it. And now we're throwing a little curveball in there and saying, all right, we lied a little bit. Actually, you're going to find we lied a lot by the time you finish. I mean, you're going to graduate someday and look back on this class and, man, that Dr. Young, he pulled a lot of lies, didn't he? All right. All right. Well, if it helps, it was for your understanding. It's like telling your mom you haven't gotten her a Mother's Day gift yet. Right? You're, of course, telling a little white lie for her benefit. Because you have gotten it already, I'm quite sure. All right, anyways, all right. So now let's change this. Let's go back to the problem I mentioned before here. Let's put in some numbers that are 3/4 the speed of the light. Now you'll see the advantage here. Let's say that this train is going 3/4 the speed of light. And the bird, as seen by me, is leaving the train at 3/4 the speed of light. What speed do you see? Well, 3/4 the speed of light is the speed I see the bird. The train is going 3/4 the speed of light. Downstairs, you're going to see that this extra piece will matter. You will have 3/4 the speed of light times 3/4 the speed of light divided by the speed of light squared. Of course, the top is 1.5 c, the stuff we would have expected to get without this additional piece. Down here, what is 75 squared? 0.75. Yeah. So 0.565. And so when I finish my calculation and go 1.5 divided by 1.5625, I get 96% the speed of light. And nope, it did not go faster than the speed of light. And we could try this with 80% the speed of light, 90% the speed of light. In fact, why don't we change it all together? Let's do this. Forget the bird. Let's say I have a flashlight. I am traveling at some speed v, any speed you want it to be. It could be a small speed, it could be a large speed. Let's just call it v. So here I am in my train going the speed v, and I take a flashlight and I shine the flashlight, and the light goes away from me at the speed of light. What do you see? Well, let's try it. All right, I shine the flashlight. I see a speed c. I am traveling in my train at some speed v, great or small. I divide it by 1 plus v c squared. I can write that as factoring out a c and then 1 plus v over c in the numerator. Because in the denominator, I have 1 plus v over c. Look what happens top and bottom. What speed do you see? C. And so no matter what speed I'm traveling, if I turn on the flashlight and see the speed of light, what do you see? Oh, isn't it brilliant? Everybody's going to see the speed of light. And this is the correct formula that would get everybody to see something that's traveling the speed of light, traveling the speed of light.
two equations that we came up with, where it's the minus VU over C squared. The U's in the X direction, right?
Oh,
Sub X.
yep. Everything I've done sub x. Now, even though I didn't get nearly done as much as I wanted, let me do this. Before I lose all of your attention, because I think this one throws it even worse. What about the vertical speed of the bird?
Are you moving relative to the vertical speed of the bird?
You see, in the old system, it had the same vertical speed, right? And I'm glad you asked that question. I'm not even moving in the vertical speed, am I? I am moving horizontally. So does that simply mean that the vertical speed that I see is the same vertical speed that you see?
Yes.
No. Because come back to here. What affected the speed? Space and time. Now, because it's the vertical and I'm moving horizontally, the space is not affected, but time still is. Oh, darn. So, I guess I have to ask this question. What speed in the y direction would you perceive of the bird compared to what I perceive of the bird? And I have erased my transformations, a bummer, but this could be the same as dy prime. No problem there. The dt was the gamma dt prime plus v dx prime c squared. I think that's what we had over here, right? Yeah, the dt. There is my transformation. So when I multiply top and bottom by 1 over dt prime, the numerator is going to give me the velocity in the vertical direction. The denominator is, of course, the added piece here. This is the transformation, if you will. This is the time dilation.
Sub Y.
And what's interesting is it's sub x, right? In other words, what speed do you see for the vertical motion of the bird is kind of what I would see for the vertical motion of the bird, but because of the time dilation, you get a different number. And you get a smaller number. And interesting enough, the time dilation is caused by the motion in the x direction. So, it's different. And I guess we'll leave it there. Yeah, question.
You know what axis is what axis?
Well, the x-axis is defined as the axis that the other observer, is on. So the bird may be moving with me or perpendicular to me.